This is Mr. Wilson with the first unit of Physical Science B, and I'm going to give you an overview of waves today. So, what is a wave? In general, or I guess to be specific in science, it's a rhythmic pattern of energy that moves through a material. You all know what waves are. You've seen them 1,000 times. Basically, it's energy moving through something. It's how we see the energy. The stuff that it moves through we call a medium. The medium can be any kind of material. It could be a solid, a liquid, a gas. It could be anything that the wave moves through. Now, one thing I need you to understand about this stuff, though, is that the medium does affect how the wave travels through it. Since the energy is moving from molecule to molecule inside the medium, however that medium is, impacts how the wave travels. So there are two things that are important here. The first is the temperature of the medium. If the temperature is higher, those molecules are moving a little bit faster and they're going to run into each other a little more frequently, which makes it easier to transfer the energy. So waves generally move faster through things that are hotter. The other thing that plays a role here is the phase of the medium. Again, since energy is being transferred from molecule to molecule here, solids tend to have faster waves in them than gases do because the molecules are closely placed together. Okay, there are two types of waves that we need to worry about, and the first is called a transverse wave. Transverse waves are waves in which the energy that they are carrying moves perpendicular to the medium that they are moving through. Here is an example of a transverse wave. The energy is moving from left to right, but notice how each of the little individual molecules within the medium are just moving up and down as the energy moves through it. The medium is moving perpendicular to the movement of the energy. Now here is a more general look at a transverse wave, and I wanted you to see this because these different sections have names. First, we have the crest. The crest is simply the high point of the wave, the highest point. By the way, this dotted line here represents the steady state of the medium without any energy flowing through it. The next portion of the wave is called the trough. The trough is just simply the low point of the wave. Wave height is called amplitude, and it's a measure of how much energy there is in the wave. The higher the amplitude, the higher the waves in effect, the more energy that they are carrying. And finally, we have wavelength, and just like the name suggests, it's the length of the wave. A more precise definition would be that it's the distance between the same part of adjacent waves, or it's the distance from a point on one wave to that same point on the next wave. My second kind of wave is called a compressional wave. Now, compression means pushing together, and that's what these compressional waves do in effect. These are waves in which the energy carried by the wave moves in the same direction as the medium, because the medium kind of moves back and forth instead of up and down. All right, here is a picture of a compressional wave. And I want you to focus your attention on one of the red dots. Notice how the red dot is moving. All the other little dots are moving in the same way, but they're a little harder to follow. But notice that the red dots are moving back and forth in the same direction that the energy is moving through the wave. Now these waves too have specific portions that you need to know about. The first one is called the compression. Again, compression means pushing together, and that's the part of the wave where the medium is pushed together. And in this picture, that's why it looks like it's a little darker here, because all those medium molecules are being shoved together, and it's causing it to be a little denser. The area where it's spread out is called the rarefaction. So essentially, in this section of the rarefaction, there's little or no medium because it's been spread out so thinly compared to the compression where it's densely packed together. This too has a wavelength, and it basically amounts to being one compression and one rarefaction together make a wavelength, but it's the same idea. The point on one wave to that same point on the adjacent wave. All right, there's one more thing I want you to get with these two waves. Notice this picture. Here I've put the transverse wave next to the compressional wave. Notice that where I have a trough on a transverse wave, it corresponds to the rarefaction on the compressional wave. And notice too that the crest on the transverse wave corresponds to the compression here. I want you to see that correlation because that exists all through these waves. The crest is to the compression as the trough is to the rarefaction. The density of the compaction or the compression corresponds to the amplitude or the amount of energy that's there, and it's harder to see in these waves, but it's still there too. We just don't tend to label it on these types of things. All right, thank you.